3.6 is about inverses. This is something that you learned previously. Some of it might have been from Algebra 1, but you definitely covered this in Algebra 2. We also kind of touched on what an inverse function was with our reaction time lab in class, because we were using an inverse function of the vertical motion equation. So we're going to go a little bit more into the 3.6 topics when we get back to class, but for right now we just need to review a little bit of what you've learned before. Mathematical inverses are functions where the input and output have been switched. This means that the domain and range will also be switched. This has a special notation where we use that -1. It almost looks like an exponent, but we're not raising anything to the -1 power. It's just the notation that's used for all inverses. It says this inverse, or this function, is the inverse of a function with the same letter name. So that little function, and there's the name. I mean, this could be anything like, the inverse of g of x. It could be anything. We'll use this again when we get to trigonometry as well. So just a reminder of the steps we go through when we're finding the inverse function. You start off by rewriting it out of function notation back into y equals. Then you can switch x and y, and solving for y, then you can get it back into function notation. Let's do a couple of examples of finding inverse functions. So we're going to rewrite it as y equals, switch x and y, solve for y, and once we get y by itself, we can rewrite in function notation, and I'm going to kind of clean this up, and that needs a little -1 there. So we have 1/5 x plus 3/5, and that looks more like a function, like the way we normally see linear functions. This one's a little bit more complicated. We have some exponents and things here, so we're going to rewrite it into y equals, switch the x and y, and then we're going to go through a little bit of the work that it takes to get y by itself. So I'm going to clear the denominator. I'm going to distribute so that I can deal with each term individually. I'm going to switch these two terms so that I have all the y cubes on one side. Now I can factor out a y cubed. And I can isolate y cubed. And then take the cube root of everything. Getting a little squished here, but we get y is equal to the cube root of -5x minus 1 all over x minus 1. And no, I can't cancel anything in here. So back into function notation, which I will do up here, we have h, the inverse of h of x is equal to the cube root of -5x minus 1 all over x minus 1. So a function and its inverse will perfectly undo each other algebraically. That means if we have a composition of a function and its inverse, when we put x in, we'll just get x back out. So we can confirm and verify that two things are inverses algebraically by doing a composition. So f of g of x should equal x, and g of f of x should also equal x. We only really need to test one of those. I would rather input this one into here because I notice that those 5s are going to cancel out. So that's what I'm going to do. I'm going to do f of g of x. And I'm going to get 5 times x plus 3 over 5 minus 3. And the 5's cancel, so we get x plus 3 minus 3. And we just get x. So yes, they are inverses. In geometry, you might have learned about the reflection over the line y equals x, where you just had to switch the x and y coordinates. Well, that's what an inverse is. So when we want to find the inverse of an entire function, we can reflect it over that line as well. So the line y equals x runs right up the middle. The example here, we're going to take the inverse of x cubed. So the x cubed graph looks like that, real rough sketch. So when we do the inverse, I'm just going to do my best to reflect it over that line, so that piece is reflected and that piece is reflected, and then all together we have our inverse graph. It's the one in blue.